About assignments? No? And projects, I think, we had posted the guidelines, right? The guidelines are already online, but I thought, several of us, several of my students, collaborators, had a number of open problems, so we thought we'll post them as well. So we're collecting that. I'm trying to crowdsource and collect some of those. So we'll post that as suggestions. I think these are some great directions to pursue that could result in a full-fledged paper, if you pursue that more. There is, something that's more well-defined for a course project, but there's potential. It can go further. So there'll be a list of problems stated there. But, you're, of course, welcome to use problems from your own research that you think will be very relevant to this course. So hopefully by the next few days we'll post it, and maybe we should Shaheen, online, maybe give a deadline of an initial very quick project proposal, right? Before they make the presentation. Maybe even just an abstract style proposal, just one paragraph or so, describing the problem, why it matters, what you hope to solve. So that way, if we see proposals that we think are not a good fit for this project, or we think is too simplistic, does not kind of be on equal footing with what others are doing, we'll try to call that out early enough so you can pursue other ideas. So that's so we'll post it within the next few days, and then maybe we can give the deadline sometime next week to present that abstract, and then the midterm presentation can happen, I think, sometime in early February. So we'll again clarify those dates and clarify the order, so you'll know when to present. Any questions about that? So I wanted to give the heads up, so expect on here some project ideas. So let's go back to recalling from last lecture first before we jump to an even harder problem when it comes to optimization, what I broadly call competitive optimization or multi-agent optimization. But before we get there, I want to make sure from last week we are at least clear in terms of the ideas of why non-convex optimization is just so challenging, and what are some tools we have to provide guarantees, right? When we are not going for global optimality, what does different notion of local optimality mean? What are the conditions for local optimality, and how do we achieve that? So let me do a quick recap of that, and then we can expand it to multi-agent optimization. Right, so if you recall from the last week, the idea was when the loss function does not have convexity, you have to look at weaker notions, and what we found was there's the first order convergence and second order convergence. Right, so most of the time we'll just limit to the two because it's just too complicated to think about higher order. Right, and the first order was saying the gradient should vanish, and that's a stationary or a critical point. But then it need not be a stable point in terms of, if you perturb it, it need not be locally optimal, right? So, and that's why first order was not enough, and you could have these saddle points where in some directions the objective function is improving, but in others the objective function could get worse, right? So, even locally it's not a stable point, and you don't want, in general, such points to converge to. So a lot of the lecture was asking about how to avoid these saddle points and how to converge to a locally stable point. So usually what we call a second order optimal point, or the alternative term is local stability. Because locally in that neighborhood, you cannot do better. And so you at least would like such a point. And so that was kind of the main goal of the lecture was, can we not only avoid saddle points, but ensure we can do it with good rates, right? Because if, gradient descent, if you land on the saddle point, the idea was you cannot move away from it because the gradient is 0, so you're stuck there. But then even if you're slightly away from it, then you could argue that you won't directly be stuck there, but it could take a long time to move away. So the idea is, of course, with 0 probability would be landing directly on a point, right, because it's a single point. But the whole idea is how are we slowed down in the neighborhood of saddle points, right, and how to ensure we get good rates depending on conditions like, we talked about Lipschitz conditions, both on gradient and then also on the Hessian, right? So those Lipschitz properties was ensuring that we could provide rates in terms of those parameters. And so that was kind of the high-level view, right? So the idea was, again, in terms of, like, just to recall what the saddle point was about, like the best visualization is the horse saddle, right? So whenever you want to picture a saddle point, there are directions where the function is increasing and in other directions the function is decreasing. And so we saw this kind of a non-degenerate saddle point can only be realized in dimension strictly greater than 1. So in one dimension, all you will have a degenerate point where the second derivative is 0, right? You cannot have a non-degenerate saddle point. And so the idea is as you increase these dimensions, you can have these highly complex saddle points where certain directions are increasing, the other directions are decreasing. And and part of the lecture, we also discussed why this is a big problem in machine learning, especially when we are training these highly non-convex loss functions, such as in deep neural networks, or even if you think about latent variable models. Like, whenever you have like symmetries in the system, then you can have an explosion of saddle points. But on the other hand, we would like symmetries, right? Like, if you're introducing latent variables, the idea is these are some unexplained phenomenon and how they affect the data. You could exchange the labels of the latent variables and still get the same answer. And so these two are kind of intertwined, like optimization versus the representation you would like, right? So the neural networks have a rich representation because this is highly non-convex, but it's also going to make the optimization landscape harder to understand. And so we talked a bit about this interplay, and also the main intuition here we covered was, when there are symmetries, these saddle points are inevitable, right? Because, think about like these two are equivalent points, like, because of a symmetry, there's an optimal point, or even let's say a globally optimal point here, and it's the same here when you switch, when you have this symmetry. But when you're transitioning from this spacing to another one, you will have to go through saddle points or even saddle surfaces, right? So that's kind of the idea that symmetries can lead to much more complicated landscapes with a lot of saddle points and even manifolds of saddle surfaces. So that was a rough intuition we had. And then we also said another source of getting these saddle points and even manifolds of saddle surfaces was with over-parameterization. Right? So if you're going to use a neural network with more capacity than what your true function is, so we gave this simple example where the true function was just a perceptron, right? So meaning with just this line you can separate the points. Now if you use instead two perceptrons and take the mixture of those, right, or a linear combination of those, then you have more capacity than what the true function, the true underlying data, the training data is needed to needs, right? And this can like lead to an explosion of critical points. So meaning a single critical point in the smaller network or in the realizable function can lead to a whole set of critical points in the bigger one. So again, we didn't go into the details of how precisely is that mapping, but some intuitions that the source of why we could have a lot of not only critical points but even connected critical sets in our optimization landscapes, and in fact many of them will be saddle, right? right? So there won't be stable points, and we need to ensure to avoid them. So the main kind of question then was, what are some algorithms that can be guaranteed to escape saddle points fast enough, right? So as I said, the main technical detail was in like what the rates are, right? Not the fact that it escapes, right? How fast does it escape, especially as you keep increasing the dimensions. The dependence on the dimension was kind of this open problem, and that was recently solved in the second paper. So the main kind of two different techniques we looked at here was, one was this deterministic algorithm, the other was stochastic. And I also made this comment that the optimization community has been focusing more on deterministic algorithms, right? So you assume you get the exact gradient at a point, you get the exact Hessian, but in machine learning, we'll never get that, right? Because you're always averaging over some batch of data that's not going to be the gradient in expectation, right? So there will be some noise. And so really this first technique of cubic regularization, I would say, is not well suited for machine learning, but I covered it with the idea that I think the general class of techniques is interesting nevertheless and could lead to other ideas or could be also useful in other fields. And the main technique that I really liked here was, I mean, all of this is based on Taylor series, right? Like the one thing to always think about is, you know, since we are looking at local guarantees, can we look at local expansion of our function? And if you just did first order expansion, that was gradient descent. If you did, and assume like Lipschitz bound on gradient. And if you did a second order expansion and assume a Lipschitz bound on the Hessian, then you have this cubic regularization term. Right, so assuming like this Lipschitzness that becomes an upper bound and you're minimizing that upper bound. And what we showed was that is nothing but equivalent to a regularized Newton method, where that regularization is adaptive in every step. And if you recall, we showed that Newton's method is bad for saddle points because it doesn't distinguish what's a saddle point and what's a stable point, whereas regularizing it will overcome that. And so I think there's an interesting class of techniques, and some beautiful results on like the rates, how fast you will get to a locally stable point, right? And then we saw, but the one that's really useful in machine learning is just our plain stochastic gradient descent, right? So what the second paper did was, to show that as long as STD had enough noise, so they were explicitly adding noise to ensure that you had this variance in every time step, and that ensured that you could escape. And the main intuition there is, as long as there is enough noise, right? So there is only going to be a small probability you will be stuck. Like the volume where you're stuck will be lower dimensional object, and there'll be only a small kind of area around that around the subspace where you'll be stuck. And most of the time, and that's why with high probability you can escape, and the question is how fast can you escape. So we didn't go into the details, but we provided the intuition that noise actually helps here. So, most of like optimization treats noise as a bad thing, right? There is in fact a long literature on variance reduction. So we haven't gone through it, but the idea with variance reduction is, if you're having a noisy gradient, that's bad, right? I mean, if you're doing convex optimization, that's truly bad because you're not getting the true value of gradient, so you may not be making as much progress. Whereas for non-convex problems, this can be a good thing because it will avoid saddle points in a very simple way, right? You're not having to do any more complex machinery and more heavy computation as in cubic regularization. All you need to do is to ensure enough noise. And that's also some conjectures why SGD may work so well in machine learning, right? Because, in practice, we don't tend to see a lot of slowdown with saddle points. And that's, because the empirical studies are hard to really verify very carefully in these large neural networks. I'll take that with a grain of salt, but at least I think this gives the intuition that having noise can help you in non-convex problems. So that was the overall thing. And I briefly also showed you like the idea that if you're doing distributed optimization, we didn't cover a whole lot, but the main idea is if you have multiple processors, you cannot, you'll have a communication cost, right? So at the end of each epoch, you have to exchange the gradients and you have to aggregate the gradients across all the multiple machines. Because the goal is you will get a variance reduction by combining the answers of multiple processors. But because that was expensive for communication, there was another method I showed you where you just take the sign of the gradient and then hope that this will give you a good result. And in fact, we showed there is a theory where you get a good convergence rate, you can prove a convergence rate even if you just take the sign. And that's why it's kind of also good to ask what's really needed for optimization, right? So it sounds like we're kind of decreasing the complexity, right? Like going from something like cubic regularization where you need second order information, you're regularizing with a cubic term, to just doing stochastic gradient descent and arguing that's enough to escape saddle points, and then saying maybe you don't even need that. You could just take the sign of the gradient and that could still give you good rates. And so far this theory only has first order convergence rates and the second order is still open. So we conjectured there would also be good second order rates or good escape of saddle points even if you just take the sign as long as there's enough noise in the system. But that's an open problem in terms of proving that concretely. So that's where we had stopped. I mean, I will not do this again. So before we jump to today, I wanted to broadly discuss optimization versus machine learning. And in later lectures, we'll go deeper into this because we'll ask, is optimization all we need in machine learning? Right, so I mean, there's a lot I've written there, but I mean, the very first question is it good enough just to optimize? Right, so what do you think? I mean, if I have a perfect optimizer, am I done? Why not?
You need a good out of sample performance.
Right, so you need generalization, right? And in fact, sometimes you don't want a great optimizer because you may overfit to your data, right? And this is kind of the tricky aspect because, a counter argument to that is, what if I told you the right loss function with the right regularization, then I want a good optimizer. And so when people use it in practice, it gets a bit hacky because, they sometimes hope that actually doesn't work very well, right? Because sometimes, you want to avoid certain solutions and then you hope optimizer, if it's not perfect, will do it on its own. So the many cases have listed here where you are actually hoping implicitly that it's not a good optimizer that you have at hand. Right, so the simplest setting is where you have a loss function without enough regularization, and then if you're fitting to that loss function perfectly, right, with zero training loss, then that may not generalize well, right? So, I mean, in some cases it may, in some cases it may not. But that's one example of where if you perfectly optimize, it could be a bad thing in machine learning. And we'll see in the later lectures, are there ways to design our loss functions? Are there ways to provide guarantees such that we also generalize well, right? So what would be the right regularization and how does it depend on the function class? So those are things we'll see in the later lectures. But just to keep in mind that we tend to sometimes think optimization in isolation even when we are solving a machine learning problem, and that's not a good thing, right? So that's the main message, that you want to ask yourself, is this the right loss function I've designed? And if I had a perfect optimizer, would this actually help me or hurt me? And that's why this has so many facets. And so maybe we can go over, so there's also Right, so I would say there are still many open problems. I mean, there's some theories showing like how even with these highly complicated deep networks, optimization is working, right? Like meaning you're able to get to a good training loss, but almost nobody talks about this hyperparameter magic. At least there's no good theory saying why it completely fails in a whole region of hyperparameters but works in some region. Right, so what is that right region and how to find that well? And I would say that's kind of what makes it so hard in practice to even compare algorithm A and algorithm B. Like, if algorithm A is SGD, then, and if it's ImageNet kind of benchmark data sets, then a lot of people have tuned the hyperparameters very well, so you could get extremely good results. Whereas an algorithm B is a brand new algorithm and there isn't enough computation spent to tune the hyperparameters, then it may seem like it's performing worse, but it's not very clear, right? And we currently don't have, I would say, a fair way to even a theory to kind of compare two algorithms perfectly side by side, because there is, and that's kind of makes it, and at scale, I mean, if you're doing this on a very large scale setting, how do we ensure a fair comparison? So that's why I ask you to treat it with a grain of salt when you read these empirical papers comparing different optimization algorithms. I mean, there's a whole ton of papers. There'll be papers saying, let's say this Adam algorithm works extremely well, and then there'll be another set of papers saying Adam completely fails, right? So you will see both of them even in the title. And I would say this is it's hard to kind of piece that apart just based on empirical results. And that's why I tried to cover some theoretical underpinnings, or at least some ways to analyze some of the standard algorithms. But I would say it's still fairly an open problem, right? And also the interesting thing to ask there will be like failure modes. I mean, you'll see some papers asking when does an algorithm fail? Right? And then we have to ask ourselves, is this realistic for a machine learning scenario? Right? I mean, we are not looking to solve the worst case instance, and then what is a good instance for our setup, for machine learning in practice? That's hard to say as well. Yeah, so these are kind of all, the can of worms, but I want to at least kind of talk about it before I jump to the next one. Yeah, so, so I think let me briefly kind of cover these cases. So, I think I referred to a blog post where this case 1 was covered, and there the idea was there'll be a solution where the result, like this embedding matrix, will be just a zero matrix, and that's, that's vacuous, right? You don't want that result. But you kind of hope that there will be other good solutions, so you try to initialize away from that solution and hope you get other solutions. So without going into the details of the problem, the intuition is there may be many good solutions, but you explicitly hope for avoiding certain solutions. And that's why the initialization is important, and then you have to assume it's a local algorithm, right? I mean, if the algorithm was doing something more globally, initialization would not help it in the same way. And so it's important to see what optimizer you're using and how the initialization and other regularization and other things you add will affect the optimizer, right? So it's not a modular approach. You can't say, there is my black box optimization, and then there is my design of loss function, there's my design of initializer. The two will be coupled in a strong way, and we need to think about it more. And that's kind of the second one as well. Like, you really, many times you're using this, like, black magic, right? Like, what a very good empirical deep learning person will know exactly what to initialize, what learning rates to set. So this is like this mysterious art. But that's kind of somehow, I think, some built knowledge of these local optimizers, right? Especially SGD. And if you switch that to a different optimizer, almost many of that will break down. And so it's important to kind of, not directly take a parameters of some previous model and a previous optimizer and try your own optimization algorithm. I mean, it's very tempting to do that because if you've designed a brand new optimization algorithm, you just hope you don't have to do the hyperparameter search again, you don't have to set everything from scratch, right? But taking that may mean you have terrible performance or bad performance. So that's something to be careful about, and that actually happened in our previous result, right? In this bar, in the gradient compression paper, we used hyperparameters almost straight from SGD. We used the same learning rates, and was showing quite a big performance gap. But after tuning it much more extensively, we could overcome that to almost negligible amount. And so that's why don't go by the first kind of results where you plug in known parameters from the internet, right? But at the same time, it's going to be computationally expensive if you have to do all that tuning on your own. But that's the challenge with these empirical studies. Yeah, so those are some, I would say, things to keep in mind if you're doing research in optimization and you want it to be applicable to machine learning. You want to try it out on machine learning benchmarks. It's important to keep these challenges in mind. And the last one, I won't go into it in a great detail, but there is actually a lot of beautiful theory in kernel methods and of course in linear models showing that you in fact don't want to run your optimizer to the very end, right? And this kind of goes back to the overfitting argument that you don't want zero training loss. You want to stop before. And there is some beautiful theory showing that the stopping early, like this called early stopping, is equivalent to regularizing with certain regularizers. So there's a nice equivalence class where you could just stop your algorithm on the original loss function, or you modify your loss function with a regularizer and train it to the very end, right? And that's true in the kernel setting. We of course don't know in the neural network setting what that'll be. But again, this is something people do a lot in practice. They don't want to keep training. They'll cut it off early on, and sometimes they are checking the validation set and saying, okay, maybe this is a good point, I won't train it further. Yeah, so this slide was, on purpose, very, in some sense, not concrete, but these are some, I would say, lessons learned when you're trying to go between theory and practice, right? Like you want to design good algorithms that may have good theoretical guarantees, but you want to apply them also in machine learning, if that's the goal, if you want to apply it for especially large-scale machine learning. These are some things to keep in mind. So any thoughts, questions here? Anything I missed? What did you observe in your kind of experiences? Is there something else? Like the interplay between optimization and learning. Were these points clear, or is there something we can discuss a bit more? I want this class to be interactive, right? Especially on things that are still not concrete enough and there are lots of open problems. That's when, discussion would help a lot.
I might have missed this from the first two lectures, but what's a multilingual embedding?
Yeah, so I didn't cover it in the class. So I've referred to a specific blog post where this problem is described in detail. But the main idea, right, there is like a set of embeddings in one language. Like an embedding is a vector representation of each word, right? And then there is another language with a different vector representation. And you want to align the two. And so the idea is you will come up with like matrices, right? Like how do you then you will align it in some third, another space, so you'll have these mappings like matrix A and matrix B, that would linearly transform the embeddings. And so in this case, you would have, like, let's say, U of W is the embedding of the word in language 1, and A is the matrix you would like to transform to this common space, and B is the matrix you would like from language, the second language. And let's say it's embedding it in W. So something of this sort, right? You want to minimize a loss function like this over all the words. And you could, of course, have nonlinearity and make this more complicated too. But in this simple example, the idea was you could always take A, B to be 0, right? That's a trivial solution, but that's not a solution we want. But in fact, that's even a globally optimal solution, right? So everything's 0 and you get 0 loss. And so in a way, people are designing these loss functions without kind of, what they usually do is just initialize it away from 0, right, and hope it'll go to a different basin. Or you could kind of directly also add regularizers, right? But then with the regularizer, you want it to push away from 0, and that's trickier. Usually you want it to be within a ball, and that's easier, right? So this was an example of a function where you actually don't want one of the globally optimal solutions. You want to explicitly avoid it, because that's not an interesting solution from a machine learning perspective. And so you can't treat the optimization as a black box, because let's say we had a perfect optimizer that gave an arbitrary globally optimal solution, but I want to be able to specify to it, avoid this, I don't want this one. And with local algorithms, we can do that easily, because we can just initialize sufficiently far away and then hope it will go to a different basin. But for a non-local algorithm, right, it's harder to ensure that.
Yeah. How does the perfect optimizers impact the desirable performance of something like restrictive Boltzmann machines?
So, when it comes to restrictive Boltzmann machine, again,
just like generative models in general, making it too perfect kind of prevent from getting good results.
So we'll discuss that more in the generalization lecture, but there isn't, to me, philosophically, the unsupervised or supervised that different, right? So you could have the same issue even with the generative model. You fit to your data you have so far, and you may not generalize beyond to unseen data, right? You may not truly capture the distribution of the data. And so kind of the GANs, that's why is argued as a way around that, and we'll also cover that. Any other thoughts, comments?
Another stupid question. Is unsupervised learning still within the framework of optimization?
Yeah, so we'll actually, cover the GAN at least at the high level, and we'll ask what optimization problem that leads to, right? But even more kind of before we get to a GAN, which is complicated, the best thing you would, if there is a likelihood function, right? You want to optimize the likelihood. Let's say you want to say, remember in the first day I covered a model. Right, the model was there's an observation and there's an unknown parameter theta. So this is unknown, and this is the observation. And with the maximum likelihood estimate, what you want to do is maximize this likelihood, right? You want to say, give me the parameter theta that maximizes the likelihood. Here I'm assuming a single observation. If it's IID observation, you would be maximizing the sum probability, right? So that's kind of the most standard thing you would do when there is likelihood available. When you have a specification of the likelihood, you want to maximize the likelihood, right? So this is maximum likelihood estimate. And so in that sense, yes, the optimization is very much intertwined. And more generally, you may do or rather, an alternative estimator, I wouldn't say general, is the method of moments where you're fitting moments of your distribution. So what's kind of the simplest method of moments estimator?
Mean.
Yeah, so fit the mean, right? And then what is the second order would be like the variance or covariance. And so this is nothing but a Gaussian approximation. So, but you could also go to higher order, and we'll actually cover that in 2 lectures when it comes to spectral methods. We'll ask how you can use higher order moments and extract information to get a good estimator, and what kind of estimation problems would that be.
Anima, why are you calling this the Gaussian approximation? Is it something to the Gaussian?
Yeah, because only the Gaussian distribution is specified by
By
moments,
only 2 parameters.
by only 2 moments, right?
Exactly.
I mean, if it's multivariate, it will be more than
Sure.
2. But the idea is if you're fitting your data to just the first, if you're only taking the first 2 moments of your data, right, then that's a Gaussian approximation, because only the Gaussian distribution is specified
I see, okay.
by moments up to second order. Right, and for more general distribution, you would need higher order moments. If you ignore them, you don't compute them from your data, you're missing that information. And we'll cover that in, I think, in 2 lectures and a bit in the next one too. Yeah, so it's kind of like I flipped a little bit in the sense of kind of getting to learning almost completely after these optimization lectures, right? So, but at the same time, I didn't want the optimization to be completely decoupled with learning because of exactly these kind of issues. When you get into the details and when you try to run them in practice, they will be tightly coupled. But after this lecture and maybe the next one, all of it will be focused on the learning aspect. Good. Yeah.
With respect to hyperparameters, is there, like, what's the current state of the theory that's more than just doing parameter sweeps, like optimize them?
So in terms of theory, I think there was a recent paper where, for SGD, like with a finite batch size, right, like what's kind of, in practice people do this like learning rate schedules, like if you train a deep network, you kind of try to do this kind of a learning rate, right? Like you keep some constant learning rate in some regime and decrease it and go further. And I think there's recent theory, which I haven't gone into in detail, arguing that this could be a good thing. Like, you can also show in theory that for SGD this is a good learning rate schedule. Because most of it is either like a decaying, like 1 over t or 1 over root t learning rate, which is not what we are doing in practice. And so that's the most recent one I can think of. But again, that's kind of assuming for the standard stochastic gradient descent, right? It's an open problem, especially for more complicated algorithms. How do we set learning rates? Yeah, so it's open.
Is that similar to like simulated annealing, or is that, I guess.
Yeah, so like simulated annealing, I would say is a different class, because there you're like kind of thinking about temperature. It's like, that's, I would say, is a more global method. That's not something we've covered in this lecture. But the way I think about it, I think of it in terms of smoothing, right? Like coming from, in fact, there's also called smoothing or homotopy. Simulated annealing is kind of like a more, they're related. I wouldn't say they're exactly the same, but there's. So these I would kind of put them as more global methods, because they're not just using gradient or local derivative information, right? So the rough idea is you're trying to like kind of, in the best case, what do you hope? You hope to get like a convex envelope, right? If you got the convex envelope, you will get the minimizer. But since this is hard to do, you hope to smooth it. Like, when you smooth this out, like when you add enough noise bigger than this small local minimum, it will disappear, right? And then the big one will stay. And how you add this noise, you can like kind of do this like a smoothing, like you perturb, like look at, not only evaluate the function at one point, but also in all the surrounding points, right? And try to kind of use that to smooth your function value. And yeah, so there are different ways to ensure that, right? But that's kind of a different class of methods. And I haven't seen much of that used in machine learning, and these could be the reasons. Because the way we do all the other hyperparameter magic, all the other intuitions about generalization is somehow very well tuned for local methods. So I'm not ruling them out, but we'll need to rethink almost from scratch how we apply it for machine learning. Yeah.
So at least the way that I'm thinking about it is that right now is that the loss function is a function of the data, right?
Mm-hmm.
So like right now we're assuming that the data is like perfectly generated in some, or like in some way, but if the data is generated in some different way that has some problems with it, then these places where we don't want it to work well are even more justified.
Yes, I mean that's the really the hard part, right? Because we kind of so far we said like noise, there's some variance found, and that's all like just it's some we didn't say how exactly this noise was generated, right? And in practice it's extremely complicated because every batch of data is going to have different samples, and it's not going to be perfectly IID. I mean, we're kind of, all the theory is assuming there's some magical underlying distribution and every sample is IID from it. At least that's the most standard theory, right? Whereas the way we collect data in practice is extremely biased. I mean, if you're scraping off the internet, right, that's far from IID. And that will introduce noise in very skewed ways. And that's very hard to measure. We don't have even methods to say how to ensure like good diversity of data, and that's why people like do all these randomizations before they feed the data into the optimizer, right? And then they do like these like random augmentations, like if it's computer vision, they'll add some noise, they'll clip the picture, they'll do like all these variations to try to ensure there's good diversity of data and it's not overtly biased in some ways. But it's more an art than a science at this moment. But that's precisely, I would say, the elephant in the room. Like, we are introducing noise into our stochastic gradient descent through mini batches. But how that depends on the way we collected our data and what kind of imbalances in the classes, imbalances in the latent attributes, we don't understand. That's a great point, yeah. Right, because, I mean, so far, all this theory, right, all we said was, for saddle points, we said there should be enough noise. I mean, if there's enough noise, you will escape. But there we added this spherical noise so that, we could get the concentration bounds to work well, and we could get actually nearly dimension-free rates. That's what the paper has the details. But on the other hand, if the noise is highly skewed, you can go wrong, right? You could like really get stuck and you could get slowed down. But we don't know how to go from that noise due to the data to the effect on optimization. That's very complicated. Yeah. Any other thoughts? Or any other experiences? I mean, suppose you were trying to use different optimization methods and what you saw was very unexpected, or you don't have an explanation yet.
I suppose just as someone who works more with optimization for its own sake rather than in machine learning applications, there is like considerable development of first-order solvers for constrained optimization problems.
Yes.
And those first-order solvers are kind of inspired by machine learning applications, but something funny happens where in machine learning application, if you have a constraint and you violate that constraint a little bit, you don't really care. Like
Yes.
if you were worried about some parameter being 0 and instead it's 1 and you said it needed to be greater than or equal to 2, this is not so bad. But what can happen is if you use these first-order solvers that are oftentimes developed for machine learning applications for problems where constraints matter, then you can have a bad time.
Yeah. No, that's a great point as well, right? So in most applications, we're not going to have hard constraints in machine learning. Maybe we want to we wanted to kind of roughly satisfy it. I mean, in many cases, those constraints could be prior knowledge, right? Like I expect like my parameters to be satisfying these additional conditions, but who knows, maybe that's not the perfect model. And so that's because we don't know what the true model is. We usually don't put constraints. The only place I would say, at least the one I can think of where you need hard constraints is in control problems. If you're learning for control settings, let's say a drone that's flying and you don't want it to crash, right? There are these safety barrier functions. There you want it to be strict, right? You don't want to violate that. So that's the one I can think of. I don't know if there are others with hard constraints. But that's kind of like a more interdisciplinary problem, and there's only kind of very recent work, right? So that's an area under development. But have there been like a lot of work in terms of the non-convex setting, you would say, with constraints? Or are they all mostly convex?
They almost all convex, just because they don't want the problem of finding a feasible point to be terribly hard.
Yeah.
If you have a non-convex problem, you end up using some kind of hierarchy of convex approximations.
Right.
And that's actually the case where these first-order solvers do very poorly.
Mm-hmm.
So,
Yeah. I mean, usually some of them assume like you already know a feasible point, right? You start somewhere feasible that somehow an oracle tells you, and then can you kind of keep following it and get to a point within that feasible set, a connected set. But that's the only way I've seen people try to overcome that. Yeah, and that's kind of also the reason we haven't been doing much constraint or any constraint optimization in this course. Because I think there are certainly areas like control where this would be relevant, but this is still very much emerging, and it gets hard enough without the constraints. So I wanted to cover the rest. But yeah, no, great point.
About the hyperparameter searching, so I used the package factorization machine once. I think there they use the Bayesian statistics to optimize the hyperparameters rather than the grid search. So they basically put a prior on the hyperparameter, and then they do an MCMC to search for the optimized one, which is probably less brute force than the
but it could be also expensive, right? So
it could be expensive.
There's MCMC, then there are Gaussian processes that will help try to scale it up well, and so it's not kind of universally true that will give you a
that's not universal.
Yeah. But no, these are also evolving, and I think that's interesting. Okay, good. I wanted to make sure we, had a good discussion on these points, because in the coming lectures, all these issues will come up, right? Like, what's the optimization function to use? How to ensure it generalizes well? How to ensure, right? Like, you can get what kind of good guarantees do you get? And so far, we only talked about convergence rate and optimization. So as you can see, the two literatures usually tend to be separated, because the generalization literature almost never addresses computation and how do you get to a point, right? But that's also the open problems. I mean, if you use stochastic gradient descent and not any general algorithm, what kind of regularization does that provide, right? And that's open, because in the generalization literature, we'll assume optimizer is some black box, and that can be problematic, because in practice we are not, in theory we are not exploiting the specific properties of an algorithm. Yeah, so that's where I wanted to I had intended to end last week, but obviously there was a lot of material, and so I hope this recap and this discussion helped set the ground for also the coming lectures in the course. So now let's jump to the part that's, the next step, right? So far we said one objective function, right, like minimize it or maximize it. But now if you have multiple agents, multiple objective functions, what can we really do? Right? So assume there are like now multiple problems you want to solve, but they're all coupled, right? So the parameters of one will affect the parameters of the other objective. And how do you ensure all of them are optimized? And we'll today look at a special case of that, which is just minimax. So it's minimizing over some set of parameters, maximizing on another set. And over an objective that's kind of joint on those two sets. Right? So it's a very, very special case of this general multi-agent setting, but we'll see its relevance to machine learning, especially with these recent GANs. Even this special case can be quite challenging, and so we'll mostly focus on that. Right. So let me first kind of go through GAN and then just give some intuitions how you could also have multi-agent like reinforcement learning setups, and then we'll get into the optimization part. So how many of you have seen GANs before? So that's a good proportion. How many of you have worked with GANs before? Yeah. Okay, that's good. So we'll do a detailed lecture on generative models, so I'm not going to compare in detail how does GAN relate to maximum likelihood, or how does it relate to method of moments, all these different estimators you could have, right? But broadly what this GAN is trying to do is trying to generate realistic looking images, right? So that's the goal. I mean, you have this collection of images. You want this generator to generate a new image that looks realistic, right? So the idea is if you have a whole corpus of faces, can you generate a new one that's not just a carbon copy of the training data, but that still people will believe is a real face, right? So that's kind of, the goal I think we should be very clear about. It's to generate something that's looking real, right? So, and that's kind of the goal of the discriminator, to ensure that the generator generates images that looks like the existing corpus of training images. And so where's the or I can do it that side. Yeah, so the idea is you will have like a min-max game between the generator and the discriminator. So let's say G is the generator, D is the discriminator, right? And you want to, so there'll be like, two data sets. So let's say P data is the actual training data. So this is, I'm gonna, if I say expectation over this, I mean I'm taking expectation over my training data. Right, so you want the, in expectation on the real data, you want your, let's say, let me use log, right? So d of x is the answer of your discriminator. So let's say the discriminator says whether it's fake or not fake, right? So there are kind of two settings. So you want to ask whether the generated images from your generator, does it look close to the training set or not, right? You want to be able to distinguish the two. And so what is the competition? The competition is the generator is trying to fool the discriminator, right? So generator hopes that the discriminator will not tell apart that what it generated is different from the training images. It thinks it's one of the training images, right? That's what you want the generator to think. On the other hand, the discriminator, you want a very good discriminator. You want one that can tell apart any newly generated image from your training set. Right, so and that's the competition. So the discriminator is trying hard to discriminate the generated and the training set, whereas the generator is trying to fool the two. Yeah.
Is the discriminator trained offline on the real data?
So there'll be, and that's the optimization question, right? How should the discriminator be trained? How should the generator be trained? But the answer is no. I mean, it's trained both together. And that's what makes it hard. Like you want to keep like updating both the discriminator and both the generator.
Okay, so just on the discriminator though is trying to tell the difference between a generated image and a real image. So the baseline is the real data. So how could it not be optimal to have it only trained on that, if that's what it's trying to distinguish?
But it's going to have, like, of course, limited capacity, right? It's not just like having a carbon copy of every training data here and just trying to predict. I mean, this is going to have, like, let's say a neural network, and you have to decide how big that neural network is. But indeed, if it were able to perfectly memorize every training sample here, right, in a naive way, you could say, like, oh, this is even slightly different from this training sample, so I will say it's fake. Right? But that's not the interesting setting anyway for practice, because we don't want it to just memorize everything and rule out anything that's not right. Instead, we want it to capture the overall distribution, because that would be the overfitted setting, because you're just completely, the discriminator is overfitted to the training data and says everything else is fake. We don't want that to happen. Right? But yeah, and here again you see this connection between both the optimization part and the capacity. Right? So the capacity of the discriminator matters, and if it is infinite, this is not interesting. Right? So so we'll come to the objective, but more generally there is like the multi-agent learning. Right? So the GAN is a very special case, I would say, because here you're asking the discriminator as a way to kind of test the generator, right? So, but you don't know, how to test it. The challenge comes, if I knew what was the perfect test for what's a real face and a fake-looking face, right? We humans somehow implicitly do that. If I knew what that function is, I didn't need to train, right? Because I could have just put in this function that could easily discriminate what is a realistic-looking face. But because I don't know that, I need to learn that aspect as well. And so that's kind of this minimax game where you want to kind of, be accurate on the real data. It should say like the discriminator, is real, right? So if it's 1, that means it's real. If it's, otherwise it's fake, right? So you have these two objective functions. So P latent is what's generated from the GAN, from the generator, rather. So the generator generates it, and this one you want to correctly classify it as fake. Right, so this is the log loss, and here you want to just say like, you want your discriminator to maximize its accuracy. Right? So you want it to be accurate in distinguishing fake and real, whereas the generator is trying hard to fool the discriminator. And that's why it's a min-max game.
In general, for the description of the generator and discriminator, this is a pretty abstract definition, but that generator block can be not just a neural network or some model, it can be a whole hierarchical process to generate.
Yes.
Right?
Yes. Yeah, like the way I wrote down here, this discriminator somehow is having an output that's real or not, right? All it's doing is a binary classification. And the generator is somehow giving you a distribution, right? It's having an output of images, and the discriminator is just evaluating it. Yeah, so in the most general setting, it's really about fitting a distribution, right? So, and that's kind of learning the generative process. And we'll, in the later lectures, discuss in more detail how does it relate to the classical methods. I said maximum likelihood estimation, method of moments. What does GAN really mean, right? Like, how is it different? How is it more general? What is it? So we'll hold it off until then. But there's also very nice statistical properties of GANs I think we should go into more. But that'll be a later lecture. But is the basic intuition clear on why this is a competition? Right? And, and competition need not be always good, right? You could have a very bad discriminator and a very bad generator, and that doesn't mean you will get actually good-looking images in the end, right? And that's why this is actually much harder than just single agent optimization. So people did stochastic gradient descent, everything worked mostly. I mean, they tuned a lot, they did all that magic, but that somehow made problems work. Right? And they tried to do the same with GANs, and it fails pretty badly. And so this is where I think there is still an opportunity for more sophisticated algorithms, much more open, kind of research to be done in terms of arguing when do you get to have a good generator and a good discriminator, and what is the optimization path? Like, how do you ensure it can get there?
Maybe this is like beyond the scope of the current discussion, but I mean, like using stochastic gradient descent is a natural choice for unconstrained problems. Minimax problems like this, I mean, they're precisely just another way to turn a constrained problem into an unconstrained problem. Like you could write a linear program in almost exactly this form, where like the g's or primal variables, the g's or dual variables. So if you want to solve this kind of problem globally, and I guess we don't necessarily want to do that.
I mean, we don't know how to do it, right? So in non-convex settings.
Okay, so that's the main
challenge. Yeah.
Okay.
So indeed, I mean, yes, exactly right. So I mean, if you think of these as the dual variables, then again those become like a min-max style problem. So although we didn't explicitly cover that, what you're saying is it's also relevant for constraint optimization, which is another class. So in a way, it is constrained here, right? Because it's trying to, this discriminator is implicitly trying to constrain your generator. So that's the other viewpoint I see here, because it's trying to make sure it's testing the generator in different possible ways and saying that this is a good generator. So in that sense, it's a constraint. Right, so any questions about the GAN? Yeah, so we'll look at the optimization side, and we will defer the more statistical side of GANs to later lectures. As just like a high-level intuition, right, there are, of course, much more general cases of multi-agent learning. It's not just min and max or two players. In a general case, you could have like swarm of agents, like if you're coordinating in an environment that's unknown, right? Multiple robots, multiple drones, and they can have some objectives that's their own, but also some global objective. How do you ensure that it all works out? Right? And you can have different levels of decentralization here. What kind of data? Do they see only their local data, or do they have a global view? Right? Do they see the full state, or is it partially observed? Is there going to be decision making that's global, or is it only local? Right? And many times it may be hierarchy. There's some meta agent that looks at decisions of individual ones and tries to make a global decision. And so these can get very, very complicated, right? So this multi-agent reinforcement learning, I would say there's very few works that even attempt to do that in a meaningful way, because this is hard. But kind of, this is, I mean, if you could get good optimizations, this is where you would like to get to, right? But this is still way off, is what I would say, right? In terms of making it practical enough and useful enough in a number of scenarios. So we won't talk a lot about it. Those were just some examples that I, from a CAST meeting, where these were examples of where you could have like self-assembling, like drone formations. Soonjo Chung and his lab actually looks at it in detail, how to have those formations and how to collect data and how to coordinate well. So those are actual real-life examples of swarms. And same like with, as we were saying, with drones in different scenarios, you would need to think about these coordination problems and control and decision-making all together. So that's just some nice pictures. We won't go more into the multi-agent setting because that's too complicated. Right, so now let's kind of ask, what is known, right? So, I mean, this is not new by itself to think about multiple agents, but the home of this has been really in game theory. Right? So machine learning is really not its primary home, and this is where between different fields we'd like to ask what's kind of the common tools, and but at the same time what's different, right, in the way we form problems. But anyway, I think the basic concept, hopefully everyone has done a starting game theory course, or at least, I guess, has seen Nash equilibrium before. Right? So what is the main idea behind Nash equilibrium? The idea is that no player unilaterally can improve her or his objective. Right? So unless multiple players collaborate, you can't do better than your current equilibrium point. So that's called a Nash equilibrium. So the idea is it's kind of ensuring some kind of stability, right? So if every player is making their own decisions, then the idea is if they arrive at this point, they can't unilaterally say, oh, now I'm going to move away and it's going to improve my objective. So when that cannot happen, there is interest, there's self-interest to stay at that equilibrium point. And so that's the notion of a Nash equilibrium, and that's, in many cases, that's too strong a thing to ask, right? Like, because if you can say, like, globally, there is no way to improve a loss function in the non-convex setting, that's not going to be true. So the same thing we did with single agent optimization. We said global optimality is too strong. We'll have local optimality. We can ask the same as a local Nash equilibrium instead of a global Nash. Right? And so there you're limiting the improvement to only local changes. So if you have small perturbations around the point and that does not improve your objective, right? So if you only perturb your own measurement and not anybody else's, or your own variables and not the others, then you cannot improve locally. That's called a local Nash. So if this is a differentiable game, usually we'll think of derivatives up to second order existing and bounded. Then you can describe everything in terms of the gradient and Hessian conditions. Right? So you'll see all these analogs of extending the first order and second order optimality conditions of single agent to multiple agents. And mostly we'll just look at min-max, but you could also think more generally of the same conditions.
One question. Again, that because the other way to sort of linearize these games is to use probabilistic strategies where you have everything to measure.
Yeah.
So there's something in between these two approaches of linearizing?
So you could still do that even here, right? So you could still have mixed strategies here. We are not ruling that out.
Yeah, but then one doesn't need to do local Nash anymore because then one has global Nash, right?
Yeah, I mean, assuming you can compute.
Yeah, truly you can, that's the problem.
Yeah.
I was just wondering if people have, if there are any helpful ways of combining these things, if you have a certain class of measures and use some sort of local information for this. Have you done yet?
I mean, not as far as I know in terms of the concrete, like theoretical results, right? I mean, at least in practice in this GAN community, you want to add noise, right? So it's not going to be a deterministic update anyway. So in that sense, it's a big strategy, right? Like but you're not explicitly operating in the space of measures. You're going to do a local update.
See, these are sort of very specific measures, not sort of simply all.
Yeah. But yeah, not something I've seen people characterize with. Or even like just this simple like Gaussian noise or sub-Gaussian noise. What is the impact, right, on these optimization paths? At least I haven't seen being done, which I think that may not be too hard, but I haven't seen at least but yeah, that's a great question, right? So this local Nash is saying like we'll only do local updates and you cannot unilaterally improve, right? So if you only change your own variables and keep the others fixed at this equilibrium point, you cannot have a local improvement. But the other kind of way to get around the hardness of Nash equilibrium is to have like this mixed strategies or this looking at it on a space of measures rather than on the strategies. Right, but I won't again go into that because those are usually, I mean, they're always almost hard to compute, so, but we are interested in algorithms that would be lightweight enough that we can use in various machine learning problems. So that's the, and we'll also assume differentiability, like that will also make it nice for us to kind of compare what we did in the last class and this class, right? Like again, it's all of this is really like, think about derivatives up to second order, look at the gradient conditions, the Hessian conditions, what can you see about that? So before we get into those details, right, the main thing I want to kind of contrast is there is indeed a ton of literature in game theory, but I would say much of it is not directly applicable to the machine learning scenario, right? Because I would say the single most kind of differentiating aspect is the selfishness, right? So in game theory, we are assuming these are actual human beings or organisms that have their own selfish objective. So they'll be doing some form of best response or noisy best response, right? And they won't deviate from it because at any point of time they don't want to do better. Like best response is what they can hope to do to like myopically optimize their rewards, right? And so if you assume that scenario for machine learning, that's not very applicable, right? I mean, and the generator is not some organism, at least not so far, right? So it's so we are jointly training both the generator and discriminator, and so we have the ability to ask what kind of updates should we want. And so this is where I see trouble with a lot of using like the game theory literature directly because we're going to ask to deviate from best response, and there isn't a whole lot of work that does that. So I would say that's the main kind of idea. And also, like, there's a lot of, I think, work done in game theory assuming partial information, right? So if you don't know the utility of others, you don't know like what the others are doing, then trying to understand that, right, it gives you a competitive edge. Like it's really important to try to estimate that. And whereas at least in these machine learning problems, especially the GAN problem, we don't need to do that, right? Everything's perfectly observed. We know exactly what the discriminator is doing, the generator is doing. And that's why the general multi-agent learning is extremely hard if you have partial observability, because then you're also trying to understand what the other agent is doing while simultaneously trying to figure out how to make your update, and that can be challenging. Yeah, so that's kind of like, me trying to differentiate the two threads of literature, and that's why I would say many problems when it comes to these min-max optimization problems and GANs, and more generally thinking about multi-objective optimization, but not from a selfish perspective. I think many of it is still very old. Yeah.
Would another distinction be that in many machine learning applications, studies of GANs, you tend to, like, there tends to be one of the actors or agents that you actually care about. Like, in the end, you may throw away the discriminator and use a generator or vice versa. And so you may want to skew things in a certain direction.
It's not clear, right? So that's what makes it GAN actually so hard to understand. Because I mean, if, let's say you may use your discriminator, for instance, to do distributional testing, right? Like many times, I mean, if the goal of GAN is not just to generate good-looking images and good-looking art, but to use in some downstream application, right? If we expect that this has learned the distribution well, then the discriminator could be helpful in saying, oh, this is an outlier, right? This is some sample that shouldn't be in this distribution. So people are trying to use the GANs to do those kind of tasks. And so there, the discriminator is actually more important because you're trying to come up with a test for saying whether a new sample is in the distribution or not. So it depends on the downstream task. And that's kind of a general problem with unsupervised learning, because mostly you want to not just fit a model or have a way to generate, or have a way to kind of characterize your training distribution. You want to actually generalize and use this in a downstream task. And that downstream task, right, could be very different from your objective of your generative model. And that's what makes it challenging. So we'll discuss more in the generative model section. But yeah, it's not always true that you want to only generate good-looking images. Although
that's
that's
not right. So I was going to say, just game theory treats all agents fairly equally.
Right.
And in machine learning context, it's very possible that you jump.
Yeah.
Or something.
Right. And in fact, that can change depending on the downstream task, right? And that makes it challenging. How do you relate that downstream objective back to your generative model, which to begin with is already complicated, and now you're saying now there's a different objective that will actually determine how I want to weigh one agent versus the other. And yeah, so I'm agreeing that it's hard to characterize that. But yeah, no, that's a great point too. Great. And I would say another big deviation, right, especially in majority of game theory, it's going to be like potential games. Right, in a potential game, the idea is there's some common potential function that's such that if you optimize it, it'll help everybody, right? So, like, they have some kind of common good or a common objective. There is some common objective function such that optimizing it will help everybody. And that's a rough definition. But the GAN is the opposite, right? At least, I mean, in some regimes, it's a perfect competition because improving the generator can hurt the discriminator and vice versa. So that I would say is another big challenge because if you see the literature in game theory, like potential games and near potential games is going to dominate. And
but wouldn't, for example, a downstream application be potential?
But then, so there could be multiple downstream applications, right? And the question is, can you easily specify what the downstream, how the downstream objective affects this objective? Because there is some downstream objective, but the question is, how does both the generator and the discriminator affect that? It's not clear. Right, so
basically that doesn't necessarily have gradients.
Yeah, exactly. It may not be differentiable, and how do you specify that? It may not easily be able to specify. And it may not be sometimes one task, right? So if you think about word embeddings or even the kind of GAN for images, people want to use it in multiple tasks. They want to train once and use it multiple times, and that's even more. But yeah, good point. So any other thoughts? Comments? Yeah, so go ahead.
So here we're trying to find a saddle point, but since it's non-convex, there's probably going to be a terrible number of these. If like you have a min and max, then you're going to find one saddle point. If you switch that into a max and min, you're going to find another saddle point. But there's only like 2 of however many there may be. Is there any sense of what like characteristics a good saddle point has? Like for the purpose of GANs, what mathematical properties are desired of the saddle point to translate into like performance?
No, I mean the simple answer is no, right? So because generative models in general are very hard to evaluate. And so even the question of, even a much more empirical question, right? Like how do you tell me that the GAN you have is better than a GAN in another paper, right? How do you evaluate this? I mean, people come up with these notions of like inception score and different scores that try to argue there is kind of diversity and fit, but I would say there isn't a strong foundation for evaluating this. So I guess your question kind of can be reframed as how do I evaluate that I have converged to a good saddle point, even assuming I've converged to one. But yeah, no, that's again, so I mean, you would, from the statistical perspective, what you would like is, I mean, almost this discriminator is a class of test functions, right? And you would like it to do well across the whole class. So you could come up with like post hoc tests. I mean, that's what statistics, if you've taken like I think they call it post-inference testing, if I may have, I'm not a card-holding statistician, so I'm not completely sure, but they have something like that where they finish the inference and then they try to test and see, is this a good one? Is this a good estimator? But we don't really have that kind of thinking in machine learning so far. Did you? Sarah, did you? Okay. But yeah, great question. So that's why we are going to put that all under the rug and ask, can we even expect to converge to a saddle point? Right? Like we could oscillate, we could like kind of not end up ever converging. How do we at least avoid that? So that's what the rest of this lecture will try to do. Okay, so coming to, yeah, so I mean, before we get to that point, right, so this will be the notation I'll use from so we'll post this link to this paper on Piazza, so we'll look at just the minimax game, and theta and omega are the two competing parameters. So theta is the minimization, omega will be the maximization. So I'll try to follow this notation for the rest of this lecture because that's the one in this paper. And so in this min-max setting, right, so it's, I think, easy to see that this would be the definition of local match. Right? So extending the single agent conditions to now two agents, of course you want the gradient to vanish, and you want the second order condition for the minimizer, it should be positive semi-definite, and for the maximizer it should be negative semi-definite. And it would be called a strict local Nash if these are also strict.
The negative sign you flip with the way you define the table. You want with the maximum variable.
Oh yeah, this got flipped. Yeah. Calvin. It's okay. Yeah, it got flipped, sorry. The min and the max got flipped.
Oh,
but it's clear, right? Like you want to test like only the self blocks in the Hessian. I mean, you have this Hessian matrix where, so this is something we'll use, right? Like both the diagonal blocks and the off diagonal blocks. So maybe I will put that place here to have this like the theta block means you're taking second derivative only on the theta parameters, right? And then this is the omega parameters. And so, I'm going to take this to be negative of it because I want to, that's the maximization. And then I have these cross terms. I just, what is the convention to this? So there's like the transpose of that. That's what I just go with this notation. This is minus. And so these matrices will just call it A, B, C. So just keep this notation in mind, right? So all the properties of the algorithms will be in terms of this full Hessian matrix. Because what matters is each of the self terms, like, if there was no interaction, all I needed to worry about was to ensure it's a local minimum, this is a local maximum, right? That means these two are positive definite. But now I have this interaction block, and that's what distinguishes this min-max problem from the previous class, right? So we need to really ask what is the impact of this interaction term on different optimization functions. So just keep this notation in mind, we'll not need any other complications. So any questions so far on the definition of local Nash? Right, so this is, I think, pretty straightforward. Yeah, so what's the simplest thing you can do? Oh wow. All right, so we'll take up the rest in the coming class. I'm sorry I just completely lost track. But we'll ask what is the performance of these different algorithms